Let's move from reasoning capabilities to task-specific performance evaluation, which focuses on how well models execute precise instructions in practical applications. Format compliance assessment is a fundamental metric in this domain. We evaluate how consistently models adhere to requested output structures using automated schema validation. This approach goes beyond simple pattern matching by implementing partial credit algorithms that recognize degrees of compliance rather than binary success or failure. The most sophisticated format compliance assessments include constraint violation detection systems that categorize different types of failures. For instance, we distinguish between semantic errors, incorrect information, and structural errors, correct information in the wrong format. This categorization helps identify whether issues stem from misunderstanding instructions or inability to maintain format constraints over extended outputs. A particularly valuable metric is instruction retention testing with increasing complexity. We measure how well models maintain compliance as instructions become longer, more intricate, or contain conditional elements. This reveals threshold points where performance degrades significantly. For models with tool use capabilities, we assess both API call correctness and tool selection optimality. This involves validating parameter formats and sequencing, and using decision tree analysis to evaluate whether models select the most efficient tools for each task component. Error handling and recovery quantification is another critical metric, measuring how gracefully models respond to failed API calls, malformed data, or unexpected tool behaviors. Models that can detect, diagnose, and recover from these failures demonstrate more robust tool integration. Multi-agent tool interaction presents unique evaluation challenges. Here, we assess whether models can maintain consistent context and goals across multiple tool invocations and coordinate sequences of tools to solve complex tasks. These task-specific evaluations provide insights not just into model capabilities, but into their practical utility in real-world applications. They help bridge the gap between impressive benchmark performance and reliable production deployment. Moving from capabilities to constraints, let's examine how we evaluate safety and alignment, dimensions that are crucial as LLMs are deployed in increasingly sensitive domains. Refusal consistency testing forms the foundation of safety evaluation. We use a multi-dimensional harmfulness taxonomy spanning 15+ categories to systematically probe model boundaries, from misinformation and illegal activity to discrimination and malware generation. What's particularly challenging is paraphrase invariance. We test whether models maintain consistent safety boundaries when harmful requests are rephrased using semantically equivalent language. This reveals whether safety mechanisms rely on superficial pattern matching or deeper semantic understanding. Safety threshold detection employs boundary probing techniques, where we gradually increase the subtlety or indirectness of potentially harmful requests. This helps identify the precise point at which safety mechanisms activate or fail, providing a quantitative measure of safety robustness. For comparative assessment, intermodel comparison with standardized prompting allows us to benchmark safety performance across different model generations and architectures using identical test cases. The bias quantification framework represents another critical dimension. We implement the stereotype content model from social psychology, using statistical testing to identify biased associations across demographic dimensions. We also measure representational harm through systematic evaluation of how different groups are portrayed in model outputs. This includes both explicit bias in attribute assignments and more subtle biases in scenario construction. Corference and association bias metrics detect cases where models assume relationships between entities based on stereotypical patterns, rather than contextual evidence. These evaluation methodologies not only help us measure alignment, but also guide targeted improvements to safety systems. The goal isn't perfect safety, which remains elusive, but continuously improving safety boundaries while maintaining model utility. Moving beyond alignment, let's examine robustness and reliability, dimensions that assess how LLMs perform under challenging, adversarial, or unexpected conditions. Linguistic variation resilience testing probes how well models maintain performance when inputs contain imperfections. We systematically introduce character-level perturbations like typos, homoglyphs, and alternative spellings to assess degradation patterns. These tests reveal whether models rely on superficial pattern matching or deeper semantic understanding. Syntactic transformation matrices apply controlled variations to input structure while preserving meaning. By measuring invariance across these transformations, we gain insight into a model's linguistic robustness beyond vocabulary recognition. Multilingual performance degradation is another critical dimension. We quantify how capabilities drop across languages, revealing whether models truly possess language-agnostic understanding or merely excel in high-resource languages like English. Out-of-distribution vocabulary handling assesses performance on technical terms, neologisms, and specialized jargon absent from training data. This reveals a model's ability to reason about unfamiliar concepts using contextual cues. For more targeted assessment, adversarial input generation identifies systematic vulnerabilities. Gradient-based attack methods, applicable to white box models, reveal optimization pathways that maximize error rates. These techniques help uncover potential failure modes that standard testing might miss. Universal adversarial perturbation detection focuses on input modifications that cause consistent failures across problem instances, revealing fundamental architectural limitations rather than instance-specific challenges. Instruction contradiction resilience scoring measures how models handle inputs containing conflicting directives or inconsistent constraints. This assesses metacognitive capabilities. Does the model recognize the contradiction and address it explicitly? Lastly, contextual contamination impact testing examines how misleading or erroneous information in context windows affects response quality. This helps quantify a model's critical evaluation of provided context rather than blind reliance on it. These robustness evaluations bridge theoretical capabilities and practical reliability, which is essential for models deployed in unpredictable real-world environments. While automated metrics provide scalable evaluation, human assessment remains the gold standard for LLM evaluation, particularly for subjective dimensions like helpfulness, coherence, and preference alignment. The pairwise comparison framework forms the foundation of rigorous human evaluation. We implement the Bradley-Terry preference model to convert binary judgments into global quality rankings. This statistical approach treats each comparison as evidence within a probabilistic framework, allowing us to derive meaningful scores even from incomplete comparison matrices. Statistical power analysis is critical for determining appropriate sample sizes. Unlike automated metrics with millions of examples, human evaluation requires careful efficiency. We calculate minimum required annotations to achieve desired confidence intervals based on expected effect sizes. Inter-annotator agreement, measured using Krippendorff's alpha, quantifies evaluation reliability. This metric accounts for varying types of disagreement, providing a more nuanced view than simple percent agreement. Our calibration techniques help identify and address systematic annotator biases. For specialized domains, expert evaluation systems are essential. We develop domain-specific rubrics with subject matter expert validation, ensuring criteria relevance and comprehensiveness. Double-blind annotation protocols with randomization prevent anchoring effects and other cognitive biases. Particularly for regulated domains like medicine and finance, we implement specialized evaluation pipelines with domain experts to assess both factual correctness and adherence to professional standards. Finally, we analyze correlations between expert evaluations and automated metrics to identify which computational approaches best proxy human judgment. This helps us develop more aligned automatic metrics, while reserving human evaluation for cases where automated proxies remain insufficient. The aim isn't to replace automated evaluation, but to create a complementary system that maintains human judgment as the ultimate arbiter of quality while optimizing where and how we deploy this limited resource. Let's shift focus from capabilities to constraints. Computational efficiency evaluation assesses the resource requirements for deploying LLMs in production, a dimension often overlooked in academic benchmarking, but critical for practical applications. Our throughput measurement protocol quantifies tokens per second across varying batch sizes, from single instance inference to batches of 256. This reveals how different models scale with parallel requests, a critical factor for multi-user applications. We track P50, P90, and P99 latency percentiles to characterize not just average performance, but tail latencies that affect user experience. Context window scaling efficiency measurements reveal the relationship between context length and memory consumption. While linear scaling is theoretically ideal, most models show superlinear memory growth with context size, creating practical limits well below advertised maximums. For multimodal models, we implement specialized content processing overhead quantification. This identifies computational bottlenecks in cross-modal attention mechanisms and informs optimization strategies. Hardware utilization metrics provide deeper insights into efficiency. Memory bandwidth utilization percentages reveal whether models are compute-bound or memory-bound, informing hardware selection and optimization strategies. Computational intensity analysis, measuring floating point operations per byte of memory accessed, characterizes fundamental efficiency properties beyond simple throughput measurements. For deployment optimization, we evaluate quantization impact across precision levels from FP16 down to INT4. The trade-off isn't just about speed. We carefully measure capability preservation to identify optimal quantization approaches for different deployment scenarios. As models grow increasingly complex, these efficiency metrics become essential for assessing real-world deployment viability. Even the most capable model provides little value if inference costs render it impractical for the intended application. Having explored individual evaluation dimensions, let's now examine how to integrate these into comprehensive assessment frameworks that systematize the evaluation process. Evaluation objective formalization forms the foundation of rigorous assessment. We begin by defining a capability taxonomy, with specific measurement criteria for each dimension. Precise definition prevents the moving goalposts that plague informal evaluation. Statistical power requirements and confidence intervals must be clearly specified to ensure results are meaningful. Without proper statistical design, apparent differences between models might reflect random variation rather than true capability gaps. Understanding correlation between proxy metrics and target outcomes is essential. While perfect alignment between automated metrics and real-world performance is rare, careful correlation analysis helps identify which metrics most reliably predict downstream success. For benchmark selection, sensitivity and specificity analysis helps identify evaluation suites that provide maximally useful signal. The goal isn't comprehensive coverage of all possible tasks, but rather strategic assessment of dimensions most relevant to target applications. Test set development requires methodological rigor. Stratified sampling ensures balanced representation across capability dimensions. Counterfactual test pair generation helps isolate specific capabilities by controlling for confounding factors. Adversarial example synthesis algorithms systematically probe model limitations rather than relying on random discovery of failure modes. Dataset bias detection and mitigation protocols help ensure evaluation fairness across demographic dimensions. The most sophisticated frameworks integrate automated metrics with targeted human evaluation, using the latter to calibrate and validate the former. This hybrid approach balances scalability with judgment quality, optimizing evaluation resource allocation. These systematic frameworks transform evaluation from ad hoc testing into scientific measurement, essential for meaningful comparison between increasingly sophisticated models. Let's conclude our technical discussion with methodological best practices that ensure evaluation rigor and reliability. Triangulation methodology forms the foundation of robust evaluation. By combining multiple complementary metrics that approach the same capability from different angles, we can identify convergent evidence of model strengths and weaknesses. This multidimensional approach provides more reliable assessment than any single metric. Annotation diversity is critical for evaluation validity. Demographic and expertise stratification ensures evaluators represent diverse perspectives, reducing the risk that apparent model performance reflects narrow cultural or professional biases rather than genuine capabilities. Statistical rigor requires pre-registered hypotheses and power analysis. By explicitly stating evaluation criteria and analysis methods before conducting tests, we prevent post hoc rationalization and p-hacking that can lead to misleading conclusions. Ecological validity demands real-world deployment testing beyond academic benchmarks. Models that excel in controlled environments may struggle with the messiness and unpredictability of practical applications. Deployment testing identifies these gaps before they affect end users. Reproducibility infrastructure, including containerized evaluation environments, ensures consistent testing conditions across different hardware, operating systems, and software dependencies. This prevents confounding implementation details from masquerading as model differences. Version control for evaluation datasets, prompts, and metrics prevents benchmark drift. Without strict versioning, apparent performance gains may reflect subtle changes in evaluation methodology rather than genuine improvements. Baseline comparison with consistent model configurations isolates the impact of specific architectural or training innovations. This requires careful control of hyperparameters, training data, and computational resources. These best practices transform evaluation from opinion into measurement, establishing the foundation for cumulative scientific progress in language model development. To conclude our technical exploration, let's examine emerging research directions that are pushing the boundaries of LLM evaluation methodology. Judge model architecture optimization represents a particularly promising frontier. While using LLMs to evaluate other LLMs has gained popularity, these systems require careful calibration to avoid inherited biases. Fine-tuned evaluation models develop specialized capabilities for assessment tasks, with research showing they can achieve higher correlation with human judgments than general-purpose models. Cross-model evaluation consensus protocols aggregate judgments from multiple models with diverse architectures and training datasets. This approach helps mitigate individual model biases and can identify cases where evaluations should be escalated to human review. Calibration methods for automated evaluation systems address systematic biases that emerge in LLM as judge approaches. These techniques apply corrective transformations based on human validation sets to improve judgment reliability. Measurement of evaluation model robustness to gaming is critical as model developers increasingly optimize for specific evaluation metrics. This research direction focuses on ensuring evaluation systems remain reliable, even against adversarial examples designed to manipulate scores. The multi-agent systems assessment field moves beyond single model evaluation to assess collaborative capabilities. Agent collaboration metrics quantify team performance across tasks requiring coordination, while emergent behavior detection methodologies identify capabilities that arise from agent interaction rather than individual abilities. These frontier research areas don't just improve our ability to evaluate existing models, they inform the development of next-generation architectures by providing more nuanced feedback signals. As evaluation methodologies become more sophisticated, they'll continue driving progress in model capabilities and reliability. Thank you for engaging with this comprehensive exploration of LLM evaluation methodologies. Throughout our 2 series, we've examined the multi-dimensional framework required for rigorous assessment of these increasingly sophisticated systems. We began by establishing evaluation objectives and taxonomies, providing a structured approach to what can often seem like an overwhelming assessment challenge. Our exploration of benchmark frameworks like MMLU and Helm demonstrated how standardized evaluation suites provide foundational metrics, while domain-specific evaluations for mathematics and code generation revealed how specialized testing provides deeper capability insights. The core dimensions of knowledge, reasoning, task performance, and safety formed our evaluation taxonomy. We examined how knowledge factuality assessment requires temporal stratification and hallucination detection, while reasoning evaluation has evolved from linear chain of thought to branching tree of thought methodologies. We discussed how task-specific performance focuses on instruction following and tool use capabilities, while safety evaluation requires multidimensional refusal testing and bias quantification frameworks. Our exploration of robustness testing and computational efficiency highlighted dimensions often overlooked in academic research, but critical for production deployment. The methodological best practices we covered, from triangulation methodology to reproducibility infrastructure, transform evaluation from subjective opinion to rigorous measurement. Finally, our exploration of frontier research in judge model architecture and multi-agent systems points toward the future of evaluation methodology. The field of LLM evaluation continues to evolve rapidly, with increasing focus on systematic frameworks that integrate multiple assessment dimensions. As these models become more capable and are deployed in increasingly critical applications, rigorous evaluation methodologies become not just technically important, but ethically essential. Thank you for your attention. I welcome any questions about specific aspects of LLM evaluation you'd like to explore further.